Lightning is often associated with electricity, and for good reason. It's the most obvious form of naturally occurring electrical phenomena, so it should be a good energy source, right? Why haven't we harvested power from lightning? But before we answer that question, what exactly is lightning? To produce lightning, we first need a thundercloud. High up inside the thundercloud, the air is cold enough that the water vapor coalesces into snowflakes, which then group into soft hail called graupel. In a storm, fluctuations in pressure cause high winds, often in the form of updrafts. Heavy and light graupel particles collide as they move along the updraft. When a collision occurs, the lighter particles can lose an electron, transferring charge to the larger graupel, which falls further into the cloud. The graupel in the lower region is negatively charged, and the lighter particles that move from updrafts to the higher region are positively charged. This charge separation acts like the battery that starts the process of lightning. In a real cloud, however, things can get more complicated. Wind doesn't just move up, it swirls around and graupel melts at certain temperatures, producing rain and moving some charge to the ground. But for now, we'll keep this simplified model of a dipole thundercloud, the positive pole on top and the negative pole on the bottom. The Earth will also become slightly polarized due to interactions with the dipole cloud. Since the negative charge is closer to the ground, the Earth will become more positively charged. But we still don't have lightning. Normal air doesn't conduct electricity, it's an insulator, like rubber. However, insulators can become conductors if the charge separation is high enough. The exact value at which this occurs is called the breakdown voltage. Air has a very high breakdown voltage, around 1 million volts per meter at the altitudes of thunderclouds. So we need a lot of charge to build up. After a certain point, we start to notice something interesting: electrical breakdown. During electrical breakdown, air starts to ionize, turning into a hot soup of free-floating ions or charged particles. This highly conductive plasma moves in discrete steps within channels. The plasma channel reaches temperatures of around 30,000 Kelvin, hotter than the surface of the sun. Each of these channels is called a leader. They can split off as well, which will cause the branches of the lightning. As the plasma leader moves, it searches for a well of opposite charge to interact with. For example, the leader may form from the negative region at the bottom of the cloud and move down towards the positive Earth. The positive Earth will produce a streamer, a small channel that moves up to meet the leader as it gets closer. When the two connect, boom, lightning. The leaders themselves are very hard to see, but the return stroke, the movement of charge flowing along the conducting plasma channels, occurs faster, at around one-third the speed of light, and is much more visible. In the return stroke, electrons move extremely fast to whatever new source until the voltage difference drops below the breakdown voltage, and the conducting channel can't sustain itself. As this current flows, collisions with air particles create resistance, losing energy in the form of heat, light, and sound, all the things we associate with lightning. Well, why don't we harness this energy? Well, now we need to talk about energy. Energy comes in all different types. It's actually pretty easy to get energy. It's a different question to store and distribute energy efficiently. Energy is conserved, so what do we mean when someone is consuming energy? The energy has just been converted into a less useful form by releasing heat. So you want energy that hasn't already degraded into heat. For example, meat from a cow has energy, or calories if you prefer. But the cow got this energy from the grass, which in turn got its energy from the sun. If you follow most forms of energy on Earth, you'll eventually get to the sun, which undergoes nuclear fusion to send energy to Earth in the form of light. In each step, from the sun to the grass to the cow, the usable energy is less, often a lot less. So why doesn't everyone use solar power if it's the purest source? The reason is storage. Solar provides sufficient energy, but only if we use it quickly after it's obtained. Batteries are fine for small things like a TV remote, but aren't great on a large scale. Batteries decay or leak energy, and it's this leakage that is problematic. That's why more stable things like gasoline are preferred. In large quantities, it stores energy very well. So when you use an outlet, a power plant converted some natural gas into electricity earlier and sent it to a power grid, which then metered out large voltages into much smaller voltages to your outlet that whatever you're plugging in can handle. That's a large reason why natural gas is still so dominant. Despite its impact on the environment, it's better for energy storage than wind or solar, although there are also economic factors. What we need is more research on efficient energy storage, not necessarily cleaner energy sources. But back to lightning. Where does lightning fit in all of this? Well, one, in terms of efficiency, it doesn't do all that great. Although the charge separation contains a lot of energy, it's better to go to the source of the charge separation, the updrafts and other winds within a storm. Why deal with lightning at all when a turbine will do? We already have wind turbines. To be efficient, they are big and placed in areas that are continually breezy, but not so chaotic that they'll damage the turbine. A storm can damage anything too light, is highly unpredictable, and isn't stationary. Let's say we do build something to harness electrical energy directly from lightning. We can do that, but the energy is delivered with extreme power, which is energy per unit time. A typical lightning bolt transfers around 1 to 10 billion joules of energy. But because it's delivered in just a few milliseconds, the power is enormous. That sounds like a lot, but it's only enough to power an average home for a few minutes. It is, however, extremely likely to damage your equipment if you aren't careful. And even if you are, it's unlikely your equipment will last too many lightning strikes. And now, where do you store this energy? There's a reason your phone battery doesn't charge super quickly, it takes a couple minutes or so. The battery that you power will also become damaged. And lastly, what about the energy in the battery? It will decay over time, so it should be used immediately if possible. But what if a person wants to charge their phone when there isn't a storm around? They have to rely on a different source. Unlike wind and solar, lightning and thunderstorms are unreliable. So the answer to why we don't harvest energy from lightning? Well, you could, but it's not efficient and it's not reliable. But wait, there's still video left. Even though lightning and energy are not as connected as people think, lightning is still super cool. Most of the cool phenomena occur from high altitude lightning. Up here, we have another source of charge, the ionosphere. This region of the atmosphere is filled with ions and free electrons that interact with cosmic rays and magnetic fields, which can sometimes cause wonderful light shows, such as the aurora borealis. Similar lights can be produced when, instead of cosmic rays from space, we have lightning shooting up from the Earth. Here we get things like red sprites and blue jets, in which electrical breakdown of nitrogen occurs just below the ionosphere, and elves, which are circular rings that propagate through the ionosphere due to sprites or jets. There's more to lightning than most realize, and perhaps that means there's still hope for lightning as a source of energy. Science and engineering are constantly growing, so stay tuned and stay curious. Hey everyone, thanks for watching. This was a video suggestion from a little over a year ago, and sorry it took so long, but thank you for the idea. Feel free to comment on things you'd like to see next. You can also visit and message me on my Instagram and my Substack, where I post notes and ideas on physics, philosophy, D&D, and all sorts of other stuff. If you're interested in learning more details about lightning, check out the notes in the description and the OSF wiki for lightning from the edge of space. I also now tutor on YZ, covering all things physics and math. And if you're new to this channel, please consider subscribing. It means a lot. Thanks.